So next I'm going to give you some notation that you can use to concisely phrase the statement that claims that two vectors are parallel. So let's say we've got two vectors, let's say they're coordinate vectors, and they have the same number of coordinates. In other words, they live in the same dimensional space. So let's say if we've got two vectors, x and y, the way I'll say this is just if x and y are both in Rn. That's just another way of saying they're both coordinate vectors and they have the same number of coordinates. It's automatic that n is some positive counting number whenever I write down something like this. Okay, so if these two vectors are parallel, in other words, if x and y are parallel, well then we write the following. We write x is parallel to y, like that. So just write two vertical lines in between them. So that's your notation for saying that two vectors are parallel. Let's practice using this. We've got four vectors in this example. You've got x, y, z, and w, and they each have three coordinates, and well, they're all laid out right in front of us. So let's see if we can identify some parallel vectors. Start by looking at x and y. Are these two vectors parallel? Well, yeah, if I multiply the vector x by the scalar 3, if I put a 3 right in front of here and I multiplied it into every single one of these three entries, this would, if I multiply them all by 3, I'd get 3 times 1, which is 3, 3 times 1, which is 3, and 3 times negative 1, which is 3, which is 3 times negative 1, which is negative 3, right? And that's exactly what the three entries of the vector y are. So really what it comes down to is the vector y is equal to 3 times the vector x. So that's enough to satisfy the definition of x and y being parallel. So we can say that x is parallel to y. And that's because, let me add a comment right below this. This is because y is equal to 3 times x. That's the reason. But this is the statement that x and y are parallel. Okay, what about x and z? Are they parallel? And the answer is, actually in this case, yes. This is an example of a vector. Well, the scalar that you can, let's back up. What's the scalar you'd have to multiply x by in order to get z as the result? And if there even is one. Well, in order to turn that 1 into a negative 2, this is a good way to think about it, I'd have to multiply the first coordinate by negative 2. So now what I should do is check that that's going to work for all three coordinates. If I multiply the middle coordinate or the second coordinate by negative 2, am I going to get the second coordinate of z? And the answer is yes, because if I multiply 1 by negative 2, the result is going to be negative 2. What if I multiply the third coordinate of x by negative 2? Am I going to get the third coordinate of z? That's the last question to answer, and the answer is yes. If I go negative 1 and I multiply it by a negative 2, well, negative 1 times negative 2 is going to be positive 2, which is exactly the third coordinate of z. So I can say, then we can say x is parallel to z. And if I wanted to give a reason, which I might as well do just to stick with the pattern here, the reason is because z is equal to negative 2 times x. All right, well, and it's worth noting that the first example, x and y, these are vectors that have the same direction. And how do I know that? Because y is equal to a positive scalar multiple of x. But in the case of x and z, z is equal to a negative scalar multiple of the vector x. So that means these two vectors, they're still parallel, but they have opposite direction. And an example of two vectors that are not parallel, well, how about x and w? Is the vector x and the vector w parallel? Well, if you just look at it carefully, I mean, start naively, don't rule anything out. So look at the first coordinate, one coordinate at a time. So the first coordinate, what would I have to multiply the 1 by in order to get 2? And the answer is 2. You'd have to multiply 1 by 2, and the result would be 2. That would work. Now, does it work for the other two coordinates? What if I multiply the middle coordinate by 2? Well, then I'd get positive 2, right? 2 times 1 is 2. But the middle coordinate of w is not 2, it's 0. So that scalar is not going to work. And so in other words, if w was going to be a scalar multiple of x, well, the scalar would have to be 2 that you multiply x by. But that doesn't work because of the second coordinate, as we just said. So that's how you can verify that w is not going to be a scalar multiple of x. And you could similarly use the same logic to check that x is not going to be a scalar multiple of w. Because if it was, well, go in the other direction. What would you have to multiply 2 by in order to turn it into a 1? And the answer is, well, you'd have to multiply it by a half. So you'd have to multiply 2 by 1/2 to get positive 1. Okay, well, does that work for the other two coordinates? And again, the second coordinate is not going to work. If I multiply 0 by 1/2, I get 0. But I'm supposed to get 1 because that's what the second coordinate of x is. So that won't work either. So the only scalar that would work for the first coordinate, to write x as a scalar multiple of w, would be a half. But it fails for the second coordinate. So for that reason, x is not a scalar multiple of w either. So neither x nor y, or pardon me, sorry, neither x nor w are scalar multiples of each other. So for that reason, we can say that they're not parallel. So for that, just use the same notation up here, but just draw a diagonal line through the parallel symbol. So you just say x and w are not parallel. And I think I'll just leave it at that. But the reason is because neither of them are scalar multiples of each other.